inspired power grid management. With that, the floor is yours.
Thanks for the introduction. Good afternoon, dear audience. Thanks for attending our talk on quantum-inspired power grid management. Before we go into the nitty-gritty, I would like to give you some information on the domain knowledge and some details that will be relevant when Fritz continues the presentation. So just to check, because I'm paranoid. Basically, there are a couple of caveats for the domain. Basically, the first one is that the transport of energy is not so simple as it might seem. For example, for the colleagues of E.ON who yesterday and today presented some stuff, I would just like to simplify it, but still keep you on that it is complex. Power flow, for example, from a power plant in the transmission grid towards downstream into the distribution grid can be approximated by grid participation factors. The power plant participates in the power flow, and if it's meshed, it basically branches out. These parameters come from a sensitivity matrix, and the grid participation factors are critical input for the part that Fritz will be presenting. Another thing is that the energy sector is transforming. You've heard it twice already over the course of the conference. I would just make the key point that large power plants will be replaced by smaller ones, and the number of power plants will increase drastically. And this will basically force grid operators like Netze BW to deviate from traditional planning schedules to basically do it round the clock every 15 minutes. And the human form of consuming electricity is basically time dependent. So at night you usually have load-based power flow from the transmission grid into the distribution grid, and during the daytimes it reverses. Another factor that makes this topic a little bit more complex and is relevant is that the participants in all of Germany's power grid are numerous. We have roughly 900 parties interacting in the energy sector, and all of these have to abide together to cooperate, share information, and so that not just a simple optimum per peer or per party exists, but that all collaborate and a more global optimum is reached. This process or participation process that basically forces all grid providers in Germany since a couple of years to cooperate for finding such curtailment optimum solutions is called the Redispatch 2.0 process. And this is basically the reason why this use case is actually investigated by us. Just a simple diagram. You start with input data, time series input data, and events. You gather this from your neighboring peer system operators, process this, generate scenarios. The focus that I want to give you here is this process step. This is the critical one, relevant for the talk. Here, basically, this is the last step where you analyze what resources in the grid, what generators need to be controlled in which way to prevent overloading of lines or realize curtailments. And the reason why this is important here, or for at least for us at Netze BW, is that the time we take for this step is crucial. The shorter it is, the more current information we can ingest, and the more actual or current basis our decision has. And then a little bit more about grid management as a whole. Why do it in the first place? The first one is, again, large power plants are replaced by small ones, and not just any power plants, but volatile power plants. And that has a nasty side effect that the capacity factor of renewable energy sources is much smaller than of traditional steam-based power plants. So for a gigawatt of renewable energy, you have to build more nameplate capacity. And this means that you have to basically, or at point in the season, you always will have over availability of generation, and you can never solve this with demand side response alone, and therefore there is a need for curtailment of generation capacity. The other one is that basically the grid expansion process is ongoing thing, but the project schedules are notoriously over time, and the reasons for them are manifold, but just earth moving crews, construction workers, permits, numerous reasons why lines under risk of overloading are even more at risk the longer the project is over time. The third reason is that, and this is something the colleagues from E.ON didn't really mention, but is a specialty in the German energy sector, is that the unbundling nature of the generation and the grid operation sector is that they basically have different goals. Just an example to illustrate that, for a generation power plant management company, it's essential to sell the energy by this power plant at the local national electricity market. They don't really take into account or care how the energy gets from the consuming source to the customers that they actually sell the energy. And that is the main source in Germany for redispatch curtailments. The last thing is why to do it is, to optimize the use of your grid resources. If you don't want to overspend, then you can use this as a tool. So basically the benefits, just to summarize, we can also support a faster ramp up of this energy sector transformation if we do use curtailment of generation, as well as keep up the business continuity. We can deliver our customers with the energy quicker in case something is overloaded. But the challenges of this topic is, well, it's a quite complex problem, and in a large grid, in a large medium or high voltage grid, you have multiple thousands of nodes and even more generators at times, and all these generators basically have to be considered with their own state variable. And the challenge now is to basically calculate an optimum for how many power plants do I curtail at what time and point over a time series, not just one point in time, and to do this while still reducing any overloads that happen and some other side effects. And again, what I stated earlier is we need the decision very quickly, and ideally we can't wait even a single minute, because then perhaps the information is already outdated, or a new event from a different neighboring system operator has already entered the realm that we need to reconsider and recalculate. And with this, I think we can basically now determine what motivated us to cooperate on this proof of concept. We want to basically be able to quickly calculate a large scale medium voltage grid with at least 1,000 generators with each 10 possible step points. And we want to achieve a solution in less than 60 seconds that is quite viable. It doesn't need to be optimal, but it, at this point in time, is more optimal than the current algorithm that we use at Netze BW. The last thing that is actually why this makes sense as a quantum-inspired approach is that we want to keep these boundary conditions. We want to keep certain lines in check so that they don't stay overloaded as well. And sometimes lines need to stay overloaded because we can't do anything. We don't have any capacity, or no generator is acting on that line. And with that, for the details, over to Fritz.
Okay, yeah, thank you. So yeah, that's just the first slide. First look is a little bit to check, how complex is this combinatorial problem? And here only the figures for a mid-size scenario where we have 60 generators, and typically they can be set in 10 different steps, different power steps. And yeah, if you want to do that in time slots over 15 minutes over the day, you have 96 time slots. And yeah, the number of combinations to do that is then the 96 with 60 zeros. And typically for one simulation of one situation, you need a second or so. So you see how much you have to compute to go through all the possibilities. So the age of the universe is about 18 digits. So it's much longer than that. And so what we need is a fast way to calculate that. And we also need a way to combine that in a linear form. We want to go to a digital annealing cubo model here. And we had first doubts about it. We looked at Ohm's law very precisely, and it's not exactly behaving additively, but our partner says to us it's very typical model to have as a very good approximation that the power changes of some generator in the grid has a proportional effect to the lines. So that is not exact, but it's especially for high loaded lines, it's a very good approximation. And we proved that in the proof of concept here also, that our results were in the limits. So then we said, yeah, then we can do something. That's very good for qubos. So we can additively have our decision variables with these effects on the lines. On the other hand, we had to look to the commercial effects of that. The financial model was here that if we decide to switch down some generators from the power they could deliver, the provider wants to have a compensation. So for his loss, we have here such discrete steps of refunding that we have to give. And yeah, the complete optimization target is here on one side to avoid overload of the net as good as possible, and also to save as much money as possible for this compensation, or to say it positively, to don't waste renewable energies. Let them through your grid as good as possible. And for that, we had a fairly elaborated QUBO model. I don't want to go through all the details. They're a little bit shown here in the background. Important is the main decision variable. We have this variable x, which for every time step and every generator has indication for the power level that is selected. So from that, most of the things can be derived. We have then a following technical y variable that's only for calculating one-time usage of a generator. That's an extra cost point. And important is then this z variable. That is another thing that we can allow under certain conditions, also for heavy pricing, the overload of some lines. If it's unavoidable, then that can be accepted, but has also an economic price in that model. And therefore are these z variables. One aspect of the model I want to show you, and that is how we just calculate these overload pricing. We have here the in red the current in a certain line. Then we have the delta ITL from x. That's our linear function to calculate the change that we do under a certain decision for the generator status. And if we subtract the maximum current for that line, then we have the amount overshooting in this moment here. And we have to pay there something. There is this rate OL. And so this is the price that we have to pay if we do this overload. And so this sum would now sum up all the overloads. But here it's also important to have, all things are falling out. And we have this z variable. Of course, otherwise, this would also benefit an underload. So, but nobody pays gets a refund if you don't have fully loaded lines. So for that reason, we have here these two variables in product. And what you see here, we have a quadratic optimization problem. And this is an indicator for us that we can have here a big advantage against linear models. So you can simply see this here from the amount of bits that are needed. So if we only have the core part with the x variables, we would only need 43,000 bits here for the problem that we have in mind. Then we have 20,000 additional z bits. So that's still okay. But if we try to formulate that with for a linear model, then we need for all combinations of x and z auxiliary variables. And that blows up the model to over 8 million bits. So no chance to solve such a model. And then we have a good indication that we can say, here it might make very much sense to go in that direction to get a benefit from that technology. Okay, so what were the results that we got out of it? Here is over a day the trace. So we used here from the Panda Power Grid, a very popular Python framework for calculation of these kinds of grids. The test case Illinois 200, something with 200 nodes and 60 generators. And you see the green line on top. That is the maximum load of any line. And first half of the day, we could bring that down to under 100%. And that was not for free. You can see down in the left corner there the costs for power generation reduction, this blue line. So we had to do something and pay something. But that's what we have planned. We wanted to avoid the overload costs, which were much higher here. And in the second half, we see a situation, as Jonas mentioned, where so much current is coming from outside that can't be influenced by our generators in our hands. So we have to leave it as it is here. So we have to pay here the overload costs. And you can see the blue line stays at the bottom. It does not try to do anything. It saves the generator costs. Of course, the overload costs have to be paid anyway. So this was a nice behavior to observe, and the result here is close to optimum solution for that day. Though we have here some overload, of course, it's coming from generators not controlled in the model. And the last thing that we had to look now is, can we do this in time? And at the moment, we are also doing here for these 96 steps a kind of decomposition. So we put some 5-minute slots into one optimization and let that run for a certain time. So we can do all 69 in one bucket, but if we let it run in a certain time, the search space is so huge that we get not so good results. And we tested that for different scenarios. So we can see here on that plot on the x-axis the total optimization time, so the time for one optimization multiplied by the number of buckets. And that should not exceed 60 seconds, 1 minute. And on the y-axis, we see the costs. And all these dots are different test cases. And you see there in this red bubble the one that we selected. We had there now 1 hour, 5 time slots in one optimization, and optimized that for 2 seconds. So we have 24 of those. 24 times 2 seconds is 48. We are beyond 60. A little bit better, we are with 3 only, but then we are with 64 seconds, slightly above. Perhaps that could also be selected. But what you also can see that the quality is near to optimum here. So if you drive this to the very extreme, it gets a little bit more reliable. The spread is a little bit less, but it does not go so much down, so that this is a very acceptable solution, which gives much benefit to the business here in right time. So that was then the selection, and with this status at the moment, we can say it's possible to put these for first networks that are applicable in the size, and can bring that also in the required time frame of 1 minute. Okay, back to you.
Just a quick recap on what we achieved in the proof of concept. We didn't quite achieve the 1,000 node and 1,000 generator goal, but what we did is we did improve the current state that we currently use and have. And now it's time, to basically go on from this and to either compensate or remove some simplifications that we introduced deliberately, and to scale this formulation to larger grids, or see if it can't be scaled farther, it needs to be divided again into sub-problems. And yeah, the last part is just to compare it with conventional technology, because this was quite a nice endeavor, quite a unique find, such a solution provided at Fujitsu. So yeah, that's basically the results. Thanks for the attention.